Hi guys, and welcome. It's week 16 of semester 2, which means we are into our last two lessons. We're looking at 119 and 120. So let's go ahead and flip over there. Lesson 119, we're graphing area and volume formulas. So again, we've worked with area and volume formulas all year. They're on your reference sheet, but how would we go about graphing those? So for this, the formula for the area of a square, area equals square, the sides are the same, side times side, or we could simplify that by saying side squared. Okay, so if we were to graph A, again, that's going to be our dependent variable, or our y, so to speak. Okay, it's going to be our output. Our input is going to be our side length, because the side length we need to know in order to find out the area. And the longer the side length, the greater the area. So this would be our input, our independent variable, our x. So that's why they have SA. If you want to flip it to x and y, just to kind of keep track. If you were graphing it in your calculator, we could do that. So if we have 1/2 squared, we get 1/4. If we have 1 squared, we get 1. 2 squared, 4. 3 squared, 9. And then you notice that it's taking this shape. It's not going up linear like perimeter or something like that would be. It still goes through the origin. If we have a side length of 0, we have no area, so 0, 0. Okay, but it's going up at this shape. If we were to graph that in here, we would just use x. So area would be the y, the side length would be squared. We use x, so we can do it in our xy coordinate plane. Then we square it. Okay. Then we hit graph, and we see that shape right there. Okay, so it's going up at this kind of J shape. Okay, it's going up exponentially because we have an exponent, which makes sense. So it's going up at an accelerated rate. It's not just linear going up the same amount each time, because we couldn't calculate, well, we could, but not right now. The slope of this, because it's going up at an accelerated rate. The volume of a cube, so volume side or edge to the power of 3, because okay, again, a cube is, we take a square and make it three-dimensional like a dice or something like that. Okay, it has 6 congruent square faces, so all the side lengths are the same. So length times width times height, or to simplify it, edge times edge times edge, edge to the power of 3. So again, E is 0, the volume is 0. So it still goes through the origin. If it's 1, 1 to the power of 3 is 1, 2 to the power of 3 is 8, 3 to the power of 3 is 27, and so on. So if we wanted to graph that one and see what it looked like, okay. E we can call x again, but instead of our exponent being 2, we're going to make that 3, and we're going to graph it. And we can even, I want to see right there. Yeah, let's zoom. If you wanted to kind of zoom in to get a more exaggerated shape. Yeah, it's still going up exponentially, but it's going to go up at even a more accelerated rate, because it's not just to the power of 2, it's to the power of 3. So it's going to be steeper. If we go back to that zoom standard, and obviously we can put in negative numbers, not for this example, but if we were to graph this in a plane, it does show up in the third quadrant as well, because we could put in negative numbers. We know in this example we can't have negative side length, so this, only the first quadrant would make sense for the example we're looking at. Okay. All right, so we will look at that practice set together. And then the last one we're looking at kind of deals with what we just did with graphing in our calculator, graphing nonlinear equations. So we do have many functions out there. They're still functions, but they're not always going to be linear. We've worked with linear functions. Again, if we go into clear this out, we do 2x plus 2 and we get a line. So it is a function because it would pass the vertical line test. Okay? But we're going to have other functions that are not necessarily linear, and yes, they still all are functions. They still have to pass the vertical line test. So let's take a look at what some of those might be. Okay, so linear makes a line. If it's a function that is not a line, then we call it non-linear. Okay, so pretty simple example, y equals 2x, x squared. We go x squared, and we graph it, and it gives us that smiley face shape. We go into our table, and it goes through the origin. Okay. 1 squared is 1, but negative 1 squared is also 1. Negative 2 squared is 4. 2 squared is also 4. So that's why it gives us this kind of mirrored image, because if we go where x is 2, y is going to be 4. If we go where x is negative 2, y is also going to be 4. So horizontal line will go through more than one point, but that's okay. That still is a function. It would still pass the vertical line test. And it's got that exponential shape in both the first and the second quadrant, as we see. So luckily, we have a calculator to help us out. The one thing that was nice about linear function is we said, well, it's a straight line, so we can get 3, 4, 5. We just really need 2 points, so we could use the intercept form in our standard equation. We have ax plus by, or ax plus by equals c. We could just plug in 0 for x, solve for y, 0 for y, solve for x. There's 2 points. We got our line. This one, we're going to need more than 2 points, because if we just plot these 2 points, well, is it a line going through them? Is there something going on between them? We don't really know. So to get the shape of this one, we'd probably want to have 1, 2, 3, 4 or more on just this side of the y-axis, and then those same ones that are being mirrored over here. We want to know what the shape is. So for a line, we always said we need at least 2 points. For some of these other functions, we're going to need a lot more than 2 to get the good idea of what the shape is. Independent, again, that's going to be our x values, our input, what are we putting in, okay, and then our dependent, or what we've called in the past our output, that's going to be our y, because we need, like for this, we need to know x to know y. Even going back up here, okay, when we need to plug in x to solve for y, I need to know what x is, so then I can raise it to the power of 2 to figure out what y is. So this is my independent, okay, or my input. My output, or my dependent variable, is my y. So usually when we make a table, even if we're going back to the last lesson, area and side length. Well, area is dependent upon the side length, so side length is my input or my x value. So I put that first in my table or in my ordered pair or whatever I'm doing. That's why I always kind of change it to x and y, just for simplicity for my own sake. But then also when we go to graph it in our calculator, we go into the y equals and we use x as our variable. It makes it easier to graph. Okay, so we go here. Well, x is my independent variable, or what we need to input to get our output. So y is our dependent, because it depends what y is based on what x is. So we look at this one, 6 over x. If we were to go graph this, 6 divided by x. Okay, we graph this one. Look at the shape of that. So it's in the first and the third quadrants. If we just zoom in on the first quadrant there, okay, where the exponential ones gave us kind of the J shape, it's kind of that same curve, but now it's going the other way. So it's going down at a decelerated rate. So we look at from 0 to 1, look at how much it's dropped. It won't even actually touch up pin 0, and it's dropped all the way down here. Then from 1 to 2, it's dropping quite a bit. But then we look way out here from, was this like 6 to 7? It's going down, but not nearly as much as it was over here. Okay, we can look at that same concept. Okay, we can't divide by 0, as we know, so that's why we get an error message. X is never going to be 0 because it can't be. 1 to 6. And then 2 to 3, we just go up in 1 in the x category, and then we drop 3. We go up one more, then we drop 1. We drop one more, and we just drop a half. We drop one more, and then it's just 3/10. So you can see that the y values are dropping, still dropping, but at a slower rate. So it's going okay, so it's decreasing at a slowing rate as we look at the shape of this curve. As we said, from 1 to 2, it dropped that much, but then from 2 to 3, it drops this much. Then 3 all the way to 6, it just drops one more. So again, we're probably going to need more than 2 points to get the shape of this graph. And then it does appear out here because we can put in negative values for x as well, and it's going to give us a negative output for y. So that's why it ends up in the third quadrant, because x is negative and the y values are negative. And this is inverse variation, which we've talked about. As x gets bigger, y gets smaller. As x is getting bigger, y is going down. So it's an inverse relationship, and we've talked about that already in the past, but we can graph those and get an idea of the shape of the graph. All right, we'll go over those practice set problems together in class, finish up our review for this last unit, take the test, finish our projects, and be done for the year. So good job.